So we were discussing normal random variables. So I defined x is normal, parameter mu, and variance sigma squared. And so mu could be any real number, and sigma is positive. And if x has PDF given by f sub x of x is equal to e to the minus. So the function is centered at mu divided by 2 sigma squared, the whole thing divided by sigma times 2 pi. And this is for x and r. And one of the things we start off with was the following, that we said z was normal 0, 1. That is, if mu was equal to 0 and sigma was equal to 1, if z has PDF given by, let's say, f of z is equal to e to the minus z squared by 2 over root 2 pi and z. And in literature, typically one refers to z as standard normal. So there are two things we did, and then the way we came to this to the distribution was this was the result by referred to as the De Morbier-Laplace central limit theorem. Which said the following, that if you take Sn to be binomial Np, and where p is between 0 and 1, so think of p as a constant as opposed to decaying with the n. So this we showed that we didn't show, we just gave a sketch of the proof that why such probabilities of Sn being between a and b, scaled by the standard deviation and centered around the mean, will converge to integral a to b e to the minus z squared by 2 over root 2 pi as n goes to infinity. This is a and b in R, and a less than. And that was the motivation for starting to study the central limit. And this sort of deviated from what we thought was when p was like lambda by n, then we had the Poisson approximation. We said probability Sn equal to k goes to e to the minus lambda power k by k factorial. This is a different approximation of the binomial, where if p was symmetric, p was equal to half, then the distribution is symmetric, and that will kind of illustrate itself in this normal random variable. Right. That's where we were at. So today I want to sort of, and then we also did several computations of the normal. I showed you several symmetric properties of the normal. So one was that I said that if you want to compute the chance that z is less than or equal to z, which is the same as minus infinity to z e to the minus x, let's say y squared by 2, let's say z less than or equal to a, sorry. By 2 by root 2 pi dz, and I showed you many facts about this. This is just essentially the area under the curve of the density function, which will look like this until the point A, wherever the point A. This was the area. This is the chance that z was less than or equal to A. And using the several symmetry properties of the density function, we showed that we showed many things. So one thing we showed was that the chance that if A is negative, the chance that Z is less than or equal to A is the same as 1 minus the chance that Z is less than or equal to minus A. So, and then we also showed the fact that if A is positive, then probability Z less than or equal to A was going to be equal to half plus 0 to A e to the minus Z squared by 2 over root 2 pi. And all this we began with the first property, that probability Z less than or equal to 0 is same as Z bigger than or equal to 0 or equal to a half. So that's how we started off this. So and then I tried to convince you that if I knew, since I couldn't do the antiderivative for this guy, if I knew all the values tabulated from the table of positive A's, I could get everybody. So because here also this resembled a positive A, right? So that's how I would compute the distribution function. So one of the remarks we made was that here has no antiderivative. So therefore, one needs to compute integrals numerically. Very good. So that's where we were at. Very good. So now let me try and illustrate some properties of the normal, both x and z. Then we'll try and sort of work through them slowly. So now the first thing I want to do is I want to show you how to compute these properties. Right? So suppose I have x is normal mu sigma squared, right? So x is normal. So let's go back to x. X is normal mu sigma squared. Then the probability of, let's say, x less than or equal to, let's say, some number, let's say b, is equal to what now? Minus infinity to b f of x dx, right? Which is the same as minus infinity to b. The density is what? E to the minus x minus mu the whole squared by 2 sigma squared whole thing divided by sigma times square root 2 pi dx. Right? That's the density function of x. Now, of course, again, now I don't want to keep on doing numerical tables for these guys. So these are centered around mu, not 0. So what you do is you convert it to an integral that involves the standard normal density function. And the way one does it is one takes a change of variable. So let's say you just make, let's say, z is equal to x minus mu by sigma. That means, if you do a 12th class ideas, dz is equal to 1 over sigma dx. And then the integral will become, so what are the limits going to be? The limits are going to be, again, minus infinity. That's no problem. When z is equal to x, b is equal to x, z is equal to b minus mu by sigma. So it's b minus mu by sigma. And dx will be dz times sigma. And then the integrand is e to the minus x minus mu by sigma is z, so it's z squared, and by 2, and then I have a sigma here and I have a root 2. So if I do a u substitution, that's what I will get. Now I can calculate sigma out. So what do I get now? This is the same as the above integral, same as integral from minus infinity to b minus mu by sigma. So let me write it clearly. So b minus mu by sigma times e to the minus, the integrand is e to the minus z squared by 2, the whole thing by root 2 pi, right, dz. So this is like the standard normal. So therefore, what have we shown now? Therefore, we have shown that probability x less than equal to b is the same as probability z less than equal to b minus mu by sigma, where z is normal 0. And we know how to compute the probabilities of z using the tables. Therefore, the key observation here is that to calculate probabilities of x being normal mu sigma squared, it is enough to calculate, or let's say tabulate numerically the probabilities of z being normal 0. Okay, that's the clear idea. Right. So let's do a couple of examples, and then I'll sort of illustrate these ideas across and how to use the tables and so on. Right. So before we do this, let me just do this. So there are these normal tables that are available for you in the book on the website. It's on chapter 5, on page 128. There's an illustration of it. So I've copied it here. Let me put this down. Let's see if I can get it here. So this is the table that is what I'm putting on. Let's erase my thing. Interesting. Okay, let's see what comes. Very good. So this is like a table I've given on the website, on the books chapter, and so this tabulates the table. So what does it do? It tabulates the probabilities of x less than equal to z. Right? But here x is normal 0, 1. So what are these? This number right here. If you look at this column, let's say you look at let's come here, or maybe let's not do this. Let's say, what does this number represent? This number represents, if you look at how to read this table, this number represents, so I come here, this person here is 1.2, right? Then I increase by 0.0, 1.22, 24, 26, and 28. So the way you read it is, you read it as in the sense that the probability that here I used x for normal 0, 1, x less than, here I have 1.2 plus 0.08, that's what I have. That's equal to the answer, approximately equal to, the answer is 0.9. That's how you interpret the table. Okay. So now tables are given, and this is how you must interpret it. So, and of course, this was just, if you wanted to do this is just the precise definition is minus infinity to 1.28 e to the minus z squared by 2 over root 2. Of course, you cannot do it for all real numbers. You just do it, you use the closest approximation you can find in the table and then use the answer. Of course, there are more and more detailed tables available as you write more and more numerically. But as of now, this is what. So let me try and illustrate the use of this table in the next example. So let's go. So example 5.2.12 in the book. So I have essentially a machine fills the bags with cashews. Let's say. So there are small plastic bags where. So the intended weight of each bag by the manufacturer is 200, let's say, grams. But the machine has some error. Okay, so machine makes error. The machine has tolerance. It can't precisely put 200. So what it does is it has a tolerance, which is normal distributed with mean, with expected value, with parameter mu equal to 200 and standard deviation and sigma equal to 4. So then someone will come and ask you the question, how likely is it that a bag filled by the machine will have fewer than 195 grams. So your machine has some tolerance, and then it doesn't fill exactly 200. It has some. It's normally distributed mu equal to 200, sigma equal to 4. How likely is it that the bag filled by the machine will have fewer than 95? Very nice. So here, let's how do you answer this question? Let's do a good question. Is this question? Answer. So here what I do is I know my y is normal with parameter 200 and sigma is 4 squared, so 16. Right? This is what I have. And what do I want to know? I want to find the chance that y is less than equal to 195. So I have to compute this. So how do I compute again? I know my mu is 216. We know by the previous calculation that this is the same as z is less than equal to 195 minus the mean, which is 200, divided by sigma, which is 4. Right? Very nice. So now, what this guy going to be equal to? This guy is equal to probability that z is less than equal to this 195 minus 200 is minus 5. So it's minus 5 by 4. But we already know from the facts of probability, density function of z and the symmetry calculation, right? And this is equal to the chance that 1 minus the probability that z is less than equal to minus of minus 5 by 4, which is just 5 by 3. So if I find out the chance that it's 5 by 4, then I compute this thing. how do I find the chance that I go to the tables? Right? So what is this equal to? 1 minus 5 by 4 is what? 5 by 4 is 4. Is like z less than equal to 5 by 4 is 1.25. Very good. So this is what I define. Very nice. So how do I find out 1.25? I go to the tables. I have the tables upstairs, right? I go to tables right here. So what's 1.2? 1.25 I have to go. So that's between 0.4 and 0.896, right? So 0.06. I take this person as the approximation. So we mark this in pink, let's say. So I take this as the approximation for. So maybe I can illustrate the table again. I can put the table again and show it to you. So I have to do this. So what I do is I copy the table again. So I have the table right here. And what I do is I notice that I need 1.25. So I have 1.2 here. I go 0.0, 0.02, 0.04. So it's between these two guys. So I'm going to take this as the approximate value for 1.2. That's all I have. Therefore, what I do is I go to my answer here. I go, this is equal to 1 minus the probability that z is equal to 1.26. That's my first approximation that I make. And that's going to be equal to 1 minus 0.896. And my answer is 0.104. So it's 0.104 chance, about 10% chance that my so about 10% chance that that my machine will be fill my bags with 5 grams less than 200. So there are 2 levels of approximation made, and then Variance. So this is how you would work with the normal tables. Very good. So let me quickly recap what I've done so far. So first I showed you that if you want to compute probabilities of normal mu sigma squared, you go and compute probabilities of normal 0, 1, and with a change of variable or use substitution, you can compute the probabilities of normal mu sigma squared. That's what I showed you on the right hand side. Now, for an example, here I showed you how to compute the probability of y less than equal to 195 when y is normal 216. So what you first do is you convert it to a probability of standard normal in the same fashion like I did before here. Then once you have that, if it's negative, you use the symmetry calculation to make it into 1 minus the chance that is less than or equal to 5 by 4. And then you can go to normal tables, which gives you the exact answer. So here I've tabulated the probability of normal being less than or equal to z, and these are the distribution functions. And if you notice that already the 0.5 is there at 0, right? So I added 0.5 to all the numerical integrals that I have to compute, and I've got the appropriate answer. Very good. Okay. So now I don't know if you noticed, I kept saying the following words. So I don't know if you noticed this when I was doing it. I said x is normal mu sigma squared, and I kept referring to mu as the mean. So I kept referring to mu as expected value, and I kept referring to sigma as standard deviation of x. I kept referring to this. While speaking. Let me try and now show you that is indeed the case. Let's try and show you that expected value of x is indeed going to be mu, and sigma is indeed going to be standard deviation. So the first observation we make is the following, that so to do this calculation, so this maybe I'll try as example 6.1.11 in the book. So first thing I will do is I will take Z to be normal 0. Then let me calculate E of Z. So what is E of Z going to be? E of Z is going to be integral minus infinity to infinity Z e to the minus Z squared by 2 over root 2 pi dz. So we already understood before, to understand this integral, to say anything about it, we have to first understand what happens to the absolute convergence of the integral. That is minus infinity to infinity the absolute value of Z e to the minus Z squared by 2 over root 2 pi dz, is this finite or not? Right? That's the first thing you have to check. So check first. So we check this to say that the integral converges absolutely. So how do you check that? So that's done by a little trick. So the trick is the following, that so this is a thing from calculus that your analysis 1 perhaps. So you just check this if it's on calculus results, basic calculus. What you can check is that if I look at the absolute value of Z, and then e to the minus Z squared by 2, this function, I have this function, this is always going to be less than or equal to, so there is a C1 positive, there's always going to be less than or equal to e to the minus C1 times Z for all Z. This is always true. This is something one has to sort of verify. Of course, it's most useful when Z is positive. When Z is negative, it's not so useful. But once you verify that, then you do the following. Then, since the integral is non-negative, this integral is non-negative, you first observe that minus infinity to infinity mod Z e to the minus Z squared by 2 over root 2 pi dz is the same as twice 0 to infinity Z e to the minus Z squared by 2 over root 2 pi z, and that's less than or equal to twice 0 to infinity e to the minus C1 Z dz, and that's fine because that's exponential, you know how to do it. Maybe I'll just work it out. So that's less than or equal to twice 0 to infinity e to the minus C1 Z dz by root 2 pi. I'll leave that out. And that you know is 2 over root 2 pi e to the minus C1 by C1 Z minus C1 0 to infinity, and that's just 2 over root 2 pi into 1 over C1 minus 0. So that's fine. So the integral does converge absolutely. I'll just rearrange this and I'll just say for all Z positive. So this is the absolute value, that's all I'm using it for. So this is true for all Z positive. Very good. Once I do that, then I know that the integral is finite, absolutely. And now I can go to E of Z and then observe the following, that E of Z is actually finite, but then E of Z, once it's finite, I can split any way I want to split it because it converges absolutely. So I have x e to the minus x squared by 2 over root 2 pi dx, which is same as I split up in two parts, minus infinity to 0, x e to the minus x squared by 2 over root 2 pi dx, plus 0 to infinity x e to the minus x squared by 2 over root 2 pi dx. And that's just cancels off, right? Because I do a substitution, y equal to minus x here. So I get the first integral is 0 to infinity y minus y e to the minus y squared by 2 over root 2 pi dy. And this one just carries on. So this carries on and comes down. And here this is because I have dy is equal to minus dx, and then I get this is equal to the two things cancels off, the blue cancels off for this, and I can see. So now if z is normal 0, 1, I have shown you that E of z is equal to 0. This calculation. Very good. Very nice. So let me now show you variance of z. So what's the variance of z going to be? The variance of z is going to be E of z minus E of z the whole square, right? But E of z is 0, so I just get E of z squared. And what's that going to be? That's going to be minus infinity z squared e to the minus z squared by 2 over root 2 pi. Now here's again a calculus exercise. You can easily show that z squared e to the minus z squared by 2 is also bounded by an exponential. So c2 bigger than 0 such that e to the minus c2z. For all z. This is for all z and r in fact, but I'll use it for positive. So now again, since it's a non-negative integral, this is just going to be equal to, like I did before, I can split up any way I want to split up. So I have minus 0, z squared e to the minus z squared by 2 over root 2 pi dz plus 0 to infinity z squared e to the minus z squared by 2 over root 2 pi dz. I do a change of variable again. I do y equal to minus z and dy equal to dz. So then if I do it correctly, I just get this is just same as 0 to infinity y squared e to the minus y squared by 2 over root 2 pi dz dy, and this hangs around as it is. Very nice. So now once I have this, I have to evaluate this. This is the same as if you just do the both integrals are the same. So I write it as twice 0 to infinity z squared e to the minus z squared by 2 over root 2 pi. So now I have to evaluate this integral. So I have to use an integration by parts idea. So what I would do integration by parts. And what do I get? I would take u of x to be equal to x, z, and v to be equal to e to the minus z squared by 2, right? So what I have here is just, if I look at it correctly, this is equal to z is one part, and let me make this in pink perhaps. Let me make this in pink maybe. Right, so I have I have z e to the minus z squared by 2. That's one part, and the other part I'll write in pink. So it's like the z here, and I have this integral, right? So minus plus 0 to infinity is equal to twice divided by root 2 pi outside, and I have a d. So this looks like my v prime, and this looks like it. So u prime is equal to is 1, and v prime is minus z e to the minus z squared. So that's what I would get. So this is again pink so that you can see it properly. Variance. Right. So now by integration by parts, what do I get now? This is like minus v prime, and then this is like uv prime is reverse. So you just get this equal to. So I would get the integrand e of z squared is equal to. I would get it as u minus v, right, from 0 to infinity, right? So I would get, and then I would just multiply the whole thing by 1 over 2 over root 2 pi outside. I'll leave it outside. And then here I would have a minus and a minus. That would become a plus, let's say. So that's like a minus. I'll leave it like this. So 0 to infinity, u prime times minus v times dz. That's what I get. But again, this u was in pink, so I just put u pink. Very, very good. So it's pink. And u prime was in pink as well. That's the pink part. And the green part remains v. So let's write with v. So that's what I would get. There's always a u prime of z here and a v prime and a v prime of z. So this, I think you can evaluate easily. So this is 2 over root 2 pi. This part right here, you would just get as this part would vanish completely. This part would be 0. You can just check it. Both at 0 because u is 0, at infinity because v is 0. So you get 0 here. And here you would get minus 0 to infinity. What is u prime z? U prime z is 1, and v of z is just e to the minus z squared. So you get minus e to the minus z squared by 2 over root 2 pi. No root 2 pi. Root 2 pi already outside. So dz. This is what I get. And now, what is this? Now I do the algebra again. So I get 2, 1 over square root 2 pi. I push it inside. 2, 1 over square root 2 pi. 0 to infinity. E to the minus z squared by 2 over root 2 pi dz. But this is the same as twice the chance that z is less than or equal to 0. And that we know is half. So 2 into half, I get is 1. Variance. So it means I've shown you that variance of z is also 1. Therefore, variance of z is 1. So in the parameter, when I say z is normal 0, 1, z is normal 0, 1. Sorry about that, my pen is leaking. Check. Oh, z is normal 0, 1. Okay. So why pen is not writing now? Let's see if it works now. Okay. Something's gone wrong. My pen is not writing. Okay. Let's see if this works. Z is normal 0, 1 means that actually mu, which is the mean of z, is in fact equal to 0, and sigma squared, the variance of z, is in fact equal to 1. So we have shown now that if z is normal 0, 1, then this characteristic cannot hold inside. That is that the 0 and the 1 can refer to the mean and the variance limit. In general, how do you observe this? Let's see. So now, suppose, so make it blue. Suppose Z is normal 0, 1. Then I know its mean is 0 and variance is 1. And suppose I take A and B in R and I let X equal to AZ plus B. So this immediately, by linearity of expectation, again my pen is giving me a problem. Let's see what happens. There's something happening. Of expectation, what would I get? Make it full screen. So this implies E of X is just A times E of Z plus B. But E of Z is 0 from the above calculation, so this is just B. So E of X is just B. Right? So if I let X equal to AZ plus B, E of Z is just very good. Excellent. The next thing you observe is by the property of variance, which we have done before, we know that the variance of X is just A squared times the variance of Z, because the B doesn't really matter. So that's the same as, that means the variance of X is just A squared, because variance of Z is just 1. So now, if X is AZ plus B, then the mean is B and the variance is A squared. Now let's try and check what is the distribution of the X. So what is the distribution of X? So distribution of X is like, so if I look at the distribution function, probability X less than equal to X, what's that going to be? That's going to be a chance that AZ is plus B is less than equal to X. And what's that going to be equal to? That's going to be equal to the chance that Z is less than equal to X minus B. Okay, I'd assume A is positive now. So let's assume A is positive by A. But this we know by definition is minus infinity to X minus B by A e to the minus Z squared by 2 over root 2 pi dz. This is just standard so far. Right? Let me move this to a little bit of center of the page so that we all sort of see it properly. Very good. So now I do a change of variable. I say I let y again equal to x minus b by z minus b. Let's say z minus b by a. So maybe the z I'll leave it in blue so that the y is the new variable. So what I get? I'll get dy is equal to dz by a. So therefore, what do I get now? That means this integrand here is going to be equal to e to the minus y is z minus b by a. Right? So I would get sorry, I want the reverse. I'm making an error. I'm sorry for that. Let me just come back here. Let me start again. So what I want is I want to make it into a normal number. So I want to make y equal to this. Is that right? No, I want to make it as Right. So I want this to be x. So I think I was right. So let's see. So if I say y is equal to z minus, I want the reverse. Sorry about that. I want the reverse. I want z equal to. So let's start again. So let's take just 1 second. I have a call coming. Urgent substitution now. This is equal to. Z is equal to, I want to say it as y minus b. So we put z in blue. Z is equal to y minus b by a. Right? That's what it is. So therefore, what I would get is dz is equal to dy by a. That's the substitution I would get. A is positive, so no sign changes. So I get dy by a here. Very good. And then here I would get e to the minus of y minus b by a squared times 2, the whole top, divided by root 2 pi. And I would get here minus infinity to just y, because we are to just x. Because when z is x minus b by a, y has to be just x. Very good. Once you do that, you observe that this is same as, I write minus infinity to x of, let's say, f of y dy, where f of y dy is e to the minus of y minus b by 2a squared, the whole squared, by root 2 pi, right, times a. But this we know is the PDF of x, is the PDF, not of x, PDF of normal with mean a, mean b, and variance a squared. Very good. So this is equal to this. Very nice. So that means this guy is the same as the probability of a normal random variable. Let's say I write it in words so it's clear. This is the probability of the normal random variable with mean b and variance a squared less than or equal to x. So therefore, what have we done? We have shown that the distribution of x is actually normal with mean b and variance a squared. So that's what the punchline is. Therefore, what we have shown is if z is normal 0, 1, then x, which is az plus b, is normal with parameters a and b squared. So here I should backtrack again. I should not say mean b and variance b squared. I should just say normal with parameters a squared, b and a squared. Normal with parameters a and b squared. But again, by our earlier calculation, we showed that e of x was indeed a, and variance of x was indeed b squared. Very nice. So therefore, when you say x is normal with mean a and normal with a and b squared, the mean refers to a and the variance refers to b squared. Very nice. So we have covered normal distribution thoroughly now, and we understand exactly how to do these probabilities. So one is that you have to use the tables, to do the normal random variable tables to compute the probabilities, and you also know that these parameters in the normal distribution are all referred to the mean and the standard deviation of the norm. So if x is normal with parameter a and b squared, then ex is a and variance is b squared. we've also shown that the normal scales nicely. If z is normal 0, 1, like I've done here, if I scale z by a and b, then x is normal a and b square. Very nice. Very good. Very nice. So that kind of concludes the discussion on normal. I have to do one calculation, and I will just sort of stop with that for the course in such sense.